Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in today's discussion we are going to start our continuation in particle dynamics, starting with the projectile motion at an angle. Okay, so what we will start today is projectile motion, right, at an incline. So far we have seen projectile motion in one-dimensional plane, that is, in along the z direction, or a ball, for example, being thrown vertically upward or downward, and so on. So now we have a projectile which is exhibiting a motion in two-dimensional plane. Let me say that our horizontal direction is the x direction and the vertical direction is the z direction. And to begin with, we have a projectile which is being thrown at an angle alpha, and we want to see how this travels. Maybe under the action of gravity it is going to, when will it eventually come down towards the earth, and so on and so forth. So let us in fact include resistance, the air resistance, in the projectile motion as well. So we are going to talk about projectile first without resistance and then projectile with resistance. So this is projectile without resistance. Okay. So to begin with, suppose we have a particle which is subject to gravity. So a particle subject to gravity is projected with a speed u, okay, subject to gravity. So which means the only force acting on the particle at any given instant of time is the weight of the particle. Okay, and then in a direction with in a direction making an angle alpha with respect to the horizontal. Okay, with respect to the horizontal. Okay, so then what we want to find out is we want to find the subsequent motion of the particle or the projectile. So we see that if we write down the Newton's second law, the force balance for this particle here, let me call this P. We see that our force balance is m times ddt of v. So v will have two components. One is the vx along the x direction, and the other one is along the z direction. So vzk, and then we have, this is equal to the weight of the particle. So this is minus mg k hat, right? So k hat. So that's the only force acting on the particle. So if we let me call this equation 1. So if we compare each of the components in 1, we see that there is no I component here. So we have that dvx dt is 0, and then from the j component we see that ddt of vz, the z component of the velocity, is equal to minus of g. Okay. Now we can quickly integrate and use some of our initial conditions. So we see that Vx is, so initially the particle is being projected along the line making an angle alpha with a speed u. So Vx initially will be u cos alpha and Vz initially will be u sin alpha. Okay. So so at t equal to 0, we have that Vx is u cos alpha, and since the change in this component is 0, we have that this component of the velocity is always going to be this constant, which is the value at t equal to 0. And then Vz is this plus u sin alpha. So we have already integrated and used the initial condition in this quantity. Okay. So then what we have is, so from here what we have is that Vz, so what we get is, so these are the two velocity components. So if we want to further integrate these two, so we have that this is dx dt is u cos alpha. So we see that x is u cos alpha times t, and from here we see that z is minus gt square plus u sin alpha times t, and the constant of integration in both the cases will be 0, because at t equal to 0 both x and z positions, or the component of the positions is at the origin of the system. Okay, so then we can quickly now solve. We want to describe the motion. See, we want to describe the motion of the system or the particle, and we have already found the x and the z component in terms of a parameter t here, well, the time t. So we would rather like to show the equation of motion completely in the form of x and z, so that way we can eliminate this intermediate parameter t. And from here we see that my equation of motion forms, eliminating t, we eliminate the parameter t, we find that z is x tan alpha minus g by 2u square cos square alpha, right, times x square. Okay. So we eliminate t and we find that these are the two components. Okay, so this is the equation of motion. Okay, so this is along an inclined plane for a system or for a particle without any air resistance, right? So now we can do a little bit of more analysis in this case. For example, finding the total time of flight of the system or of the particle, and also the maximum height reached. So we see that the maximum height reached will be when, so we see that the maximum height reached will be along the z direction. So to find that, well, we can immediately first of all find the total time of flight here, right? So the total time of flight first. So let us begin with writing the z equation again. So minus gt square by 2 plus u sin alpha times t, right? And we see that z is from here, if we set our z component equal to 0, we are going to get two values of time. One is of course t is equal to 0, the trivial case, and the other time that we get is t is equal to 2u sin alpha by g, right? And of course the height is 0 at two times, that is at initially when t is equal to 0, and that is after time t equal to 2u sine alpha. So which means that the total, so this is my time of flight, the total time it takes for the projectile to complete its journey, and then the time at which it reaches its maximum height. So time at maximum height would be half the time of flight. That is, the first half it takes to reach the maximum height, and the other half it takes back to reach the same or to travel the same distance, right? And we see that t is from here, t the time for the reaching the maximum height is u sine alpha by g, and that is what we plug in this z coordinate, and we are going to get our maximum height. That is what we are going to get, the maximum height. And also, so that's 1, that is 2, so we get the maximum height, and then we can also find the total range, or this is the total total distance traveled along the x axis, along the x axis, or along, or this is the horizontal distance. Okay, so horizontal distance will be the range. So which means that we have that the x from the equation of motion, x was u sine alpha times t, and in t we put the total time of flight, and we get that the range r, the total range r is given by u sine alpha times tf, which is the time of flight, and after processing all these quantities we get r is u square sine 2 alpha by g, u square sine 2 alpha by g. Okay, so that is what we have. So then one more thing we can do is we can find the range when the range is maximum. So max range, see, we get the max range when sine 2 alpha is maximum, right? So this is 1, or when alpha is 45 degrees. So it turns out when the projectile is at an angle of 45 degrees, in the case of without air resistance, we get the maximum range, and the maximum range comes out to be u square by g, right? So using this information in this formula for range. Okay, so that completes the analysis for this simple case. We can look at the second case where the projectile is experiencing some air resistance, right? So we see the case of motion with air resistance, motion with air resistance. Okay, so now again it is the same projectile which is being thrown at an angle, let's say at an angle alpha, and initially the speed is u, and the setup is the same, except now that there is air resistance on the particle in the form of k times v, where v is the instantaneous velocity. So it's opposing the particle at any given instance of time. So from here we can write the equation of motion. The equation of motion is m d v. So let me use the vector notation. So m dv dt is minus mg k hat and minus k times v, right? So well, k times v times m. So that is the air resistance term, and we see that the initial condition is at t equal to 0, we have x and z, the starting point is 0, and the velocity v is u sine alpha comma u cos alpha. Okay. Okay, so then what we have is we can write down the component wise equations, we can start solving, and then we arrive at the final set of velocities. So Vx, so using these two information, so we get Vx is equal to u cos alpha times e to the power minus kt, and then Vy is u sin alpha times e to the power minus kt minus g over k times 1 minus e to the power minus kt. Okay. So we see that for very large air resistance, for example, when k is large, right? So k is large, we see that the Vx component is almost negligibly small, and well, of course, both the velocities they are negligibly small. So that is a simple analysis. But when t is very long, right? When the total time for the setup is going to infinity, we also see that Vy comes out to be minus g over k, right? So at no instance that we see that the velocity goes to 0. We always have this so-called terminal velocity at infinitely long times. Okay, so then from here we can also further integrate. So integrate further and find that integrate further and find that x is u cos alpha by k times 1 minus e to the power minus kt, and y is, so we have integrated once more, used the initial condition, and then y comes out to be z comes out to be u ku sine alpha by by k square times plus g. So g is this is all inside this fraction, times 1 minus e to the power minus kt minus g over k times t. Okay. So from here we can find, again, we can do the same analysis. We can start finding the time of flight, the total range, the maximum height reached, and so on. We can quickly show that the total range is the range comes out to be the range comes from the x component, of the position vectors. But we see that in the x component we have this factor 1 minus e to the power minus kt. So this quantity e to the power minus kt was not present earlier without, that is in the case of without air resistance, right? We see that in this case the total range is less than no air resistance case by an amount this quantity. So u cos alpha by k times e to the power minus kt. So that is what we have. So the range is less by an amount which is this u cos alpha by k e to the power minus kt. Okay, so that is what we have, and we expect this is the case, that is the total air resistance, due to air resistance the range will be less, the particle is going to travel less distance, and of course even we see that even the speed comes out to be lower by this factor e to the power minus kt. Okay, so that completes our brief discussion regarding the projectile motions, and in the next setup I am going to talk about the motion of a particle along the circle, or the circular motion. So circular motion. Okay, so what we have is so we try to model the particle moving along a circle with some force, right? So we have the particle is moving in a circular orbit in inverse square field, field. And we see that we have a particle. So the problem says we have a particle P of mass m moves under gravity and uh, the gravitational force due to a fixed mass of capital M. So the idea is that we have a fixed mass maybe somewhere sitting at the origin, and we have another mass or small m which is moving due to the influence of this large mass and exhibiting some motion due to this interaction. Okay, so at origin. And then we have to show that the circular orbits with center O and any radius is possible. Okay, so we have to show that in this case of gravitational attraction, the particle of mass small m is exhibiting a circular motion of some radius. Okay, and then also we have to deduce or find the period of the orbit. We can typically think of this setup as the capital M being Sun and the small m being the Earth, the particle of small m being the Earth, and the Earth is rotating around the Sun and exhibiting some sort of a nearly circular motion. Okay, so then so in this case what we have is that the equations of motion, my equations of motion will read as follows. We have to show that this is for circular orbits. We have to show that we see that the following happens. R dot is 0 and V is R times theta dot, right? And we see that in this case, so in this case, so R dot means that the rate at which the radius is changing, the rate at which the perpendicular distance between the masses is changing. R dot is 0. So this first equation is telling me that R is capital R, which is a fixed quantity. So the particle under motion, this small mass particle P is exhibiting a motion with a fixed radius. Okay, and then what we have is, so V is equal to R theta, and then my second law shows that my acceleration is given by R double dot minus R theta dot square times, so this is the R hat component. So I am writing the formula right away from our analysis that we had done for circular motions or motion described with polar coordinates. So here we have the R component and then we have the theta component, right? So plus 2 R dot theta hat. Okay, so then we have that this is minus V square by R hat plus V dot theta hat, right? So then we have this. We also see that my acceleration is going to be given by, since this is a case of a gravitational attraction, we find that the Newton's second law yields the following relation: ma dot or ma is equal to minus m capital M g by r square. So that is my Newton's second law, right? So r hat. Okay, and then from here we see that, see now we let us in the formula for acceleration, let us plug all these relations. So r dot is 0, so r double dot is 0, and we also have r dot is 0 here, and from here we get r is, so my acceleration is the following. So this quantity is v square by r, and v dot is, well, we have v theta dot v theta, so this is not right, so this is v theta dot theta hat, right? So that is what we have. So that should be right. So v dot is r theta double dot. No, so that, I think this was right earlier. Okay, so v dot theta hat along the tangential direction, and then we see that comparing the acceleration from the gravitational force of attraction, we find that my equations read as follows. So v square by r is minus m capital G by r square, and v dot, this quantity, that there is no tangential component in the force, so v dot is 0, right? So v is also fixed. So here we have, from the second equation we find that the velocity is fixed, and from the first equation we find that v is well, I should keep the mod. I want to find the speed, right? The magnitude. So the speed comes out to be square root mg by r. Okay, solving this equation here. Okay, so that is my speed, and then one last thing, we also have to find the period of the orbital motion. So the period of the orbital motion comes out to be 2 pi by omega, or this is also 2 pi r over v. That's the standard formula, and we plug in the value of v here to find that this is 2 pi r over square root mg by r. Okay. Okay, so that is what we have, the period. And then the second thing is, there is something we want to highlight in this period. Okay, so let me write this formula in a new page, and let me show you what exactly I want to highlight. So my period comes out to be 2 pi r over v, which comes out to be square root 4 pi square. So I have kept everything inside the square root, by r cube by mg. And we see that here I see that t square is proportional to r cube, and this is one of the famous law that if you have satellites which are orbiting and showing circular motion, then the period square is proportional to the cube of the radius. This is the so-called Kepler's third law. Kepler's third law. Okay. Okay. So then what we have is, let us look at another case of a circular motion, that is the motion of a pendulum, right? Okay. So suppose we have a particle P suspended from some origin. So we have this fixed support, and from the support let us delegate a point O as the origin, and from the origin we have a mass m which is hanging via a rod, which we consider it to be inextensible and weightless, right? So we have a particle P suspended from O by a light inextensible string, okay, of length b. Okay, so this length that we have is b, and P is subjected to uniform gravity. P is subjected to uniform gravity and moves and moves in a vertical plane through O, through the origin. Okay. We have to find the equation of motion. Find equation of motion. Equation of motion. Okay. So what we have is that the equation of motion is, so we have two components which are acting as the forces on the particle. One is the weight acting vertically downward, and the other is the tension T, which is acting at some angle. So what we have is we have the Newton's second law comes out to be ma is equal to minus mgk minus t times r hat, right? So this is what we have, the total the force balance. So mg is acting downward, vertically downward, and the tension is acting radially along the string, right? And from here I can write my equation of motion along in polar coordinates. So we see that this is going to be the following. So we have minus m b theta dot square. We can start to reduce my weight component along the radial and the tangential direction. So if this angle is theta, this particular angle is also theta, and we have this component along the r direction and this component along the tangential direction theta. So we have that the radial component is going to give us that the net forces are going to be mg, so mg cos theta, so along the positive direction, minus t, right, along the inward direction or the attractive direction. Okay, and then we have the other equation is mb theta dot is minus mg sin theta. Okay, so from here I find that this is from here I find the equation of motion reads as follows. We have theta double dot, we just solve for we eliminate this t here, we eliminate t, and we find that the equation of motion is b theta double dot is equal to minus g sin theta, or the equation of motion is theta double dot plus g by b times sin theta is equal to 0. So here is what we have for the pendulum which is being acted upon by the gravity. Notice that we can quickly find if we see a special case when theta is small. When theta is small, we find that sin theta is roughly equal to theta, and what we have is that theta double dot plus g times g by b theta is 0. So this is a simple case of a simple harmonic motion, and from here I can quickly find the period. The period is going to be 2 pi by omega, where omega comes out to be square root g by b. Okay, so this is my omega square here. Okay, and then if we want to actually solve this equation of motion for large amplitude, that is large theta. So if so this was case 1. The second case is when theta is is large, it's not small, right? So in that case the equation of motion is minus g by b times sin theta. Well, theta double dot is d theta dt2, and now we can our left hand side only has theta. Well, theta is implicitly a function of time. I want to write the right hand side is a function implicitly of time. I want to write the left hand side also as a function of only the explicit variable, which is theta. So we see that theta dot is equal to d theta dt, or this is also equal to d theta. D theta, how should we write? This is going to be, no, I would rather say theta double dot is d theta dot dt, and this is d theta dot d theta times d theta dt, right? And d theta dt is the so-called omega, or the angular velocity. So this is omega times d theta dot d theta. Okay. Theta dot, so theta dot is my angular velocity omega. So we get that this is omega times d omega d theta. So we plug it here, and we see that my equation of motion is omega times d omega d theta is minus g by b sine theta, and then we can quickly integrate, use my initial condition, and to arrive at the final equation of motion, that omega square by 2 is g by b sine theta. And then we have that at t equal to 0, the initial condition, at t equal to 0 we have the angular velocity will be 0, but theta will be equal to some angle made with the vertical of the pendulum. Okay. So here we have the pendulum which is making some angle alpha to begin with, and if we plug this initial condition to find this constant of integration, we can quickly find that my equation of motion, that is omega, is a function of theta. And we can also quickly, from here we can quickly also find what is my period, right? From here to find the period, we have so omega square is going to be 2g by b times sine times cos theta minus cos alpha, right? So 2g by b, and that is after integration, and we also have that this is the square root. So this is, we integrate this once more, so d omega is d theta dt, and now we have this right hand side, and from here I can quickly find my total time which is taken to be, so my time t is going to be, after integrating, this is going to be from theta from 0 to alpha. So we have the pendulum, notice the period is going to be given by the fact that the pendulum moves from alpha to 0 and then 0 to alpha again, and again back from alpha to 0 and 0 to alpha again, right? So there will be 4 such motions. So we will have that this is going to be 0 to alpha. So dt is this quantity d theta divided by square root of 2g by b times cos theta minus cos alpha. Okay, and dt will be from 0 to 1/4. Why 1/4? Because when we are integrating from 0 to alpha, we are actually calculating 1/4 the motion of the pendulum, right? So that is going to give us, so this is going to give us the period here, and the period comes out to be roughly equal to 2 pi by square root b over g times 1 plus alpha by 16 plus order alpha cube. Okay. Okay. So we see that. So what have we got? So for small oscillations, if we have that alpha is small enough, we get back our original period to be this 2 pi by square root b over g, which was the case that we had just now seen in the first case. And so this is my more general scenario. So let us wrap this discussion of the projectile motion and the motion of the particle along the circle. And in my next module, I am going to talk about linear oscillation and how to describe these oscillations using the so-called normal mode expansion. So thank you very much for listening.